Hello my dear friends and welcome back. Informatics 2, and this time we're going to talk about queues, lesson 13. Actually, we're going to talk about queues in this lesson and in the coming two lessons as well. Let's see what we're going to cover in this class. Queues in our life. We're going to see what are the real practical applications of queues in daily life. And then after that, we're going to define queues in computer terminology and how we use them, where we use them. After that, we're going to talk about the manipulation of queues on computers. Basic applications of queues on computers, and there are many of these applications. We're going to list some of them. And then after that, we're going to define the basic operations we perform on queues. Okay, let's start from the very beginning and where we use queues in our life. Well, almost everywhere. When you go to the bank, you stand in a line waiting for your turn to be served. So we stand in a line like this, and the first person who comes in is going to be the first person who's going to be served. Okay? The later you come in the line, the longer you're going to wait till you get served. Another queue is when you go to the airport and you want to buy your ticket. When you are at the bus station and you would like to get into the bus to get to your job. That's again a queue, a line basically. Anywhere basically where you would need to go, stand in a line waiting for others to be served in front of you, that's basically a queue. So that's pretty much covers everywhere we go in our real life. Do we have something like that in computers? Yes, of course. Computer queues, it is a list like this. Very similar in a sense to the stack which we talked about in the last two lessons. However, there are some changes and variations. Basically, a queue is a list in which all insertions of entries are made at one end of the list. Insertions go here to a place where we call it rear or tail, the end of the queue. So when you come to the line, you're not going to go to the first place, of course, because there are so many people already ahead of time before you. So you're going to come and stand at the very last position in the line, waiting to be served. So that's called rear. Everybody who comes in computer terms, whenever I want to insert a new entry to my queue, that entry is going to go as a last entry in my queue. However, when I want to delete entries from my queue, then I'm going to delete them from the first position. And that's basically when I delete or remove these entries, I'm serving those people. I'm serving these entries. So basically, here's my queue, something like this. Each new entry comes to the queue is going to be inserted at the very end right here. Each time I serve one of the existing entries, then I'm going to pull it from here, remove it from here. Okay? For that, queues are called first in, first out. The first person who comes in, the first entry who gets into the queue is going to be the first one who's going to be served. If you're the first in line, then definitely you're going to be the first one who's going to be served. This is for short called FIFO or sometimes FIFO. It depends. First in, first out. This means the first item that gets into the queue is the first item served. Okay? Very simple, straightforward. It's the opposite to the stack thing we talked about in the previous two lessons. In the stack, we had a LIFO, a last in, first out, because we were stacking things on top of each other. So to access the stack, we always go to the last entry on the stack, and we pull it out or we pop it from the stack. Now the situation is different. I'm having a queue like this, queue of these pins. This pin comes first, so it was here, okay? And then another customer comes in, so he goes at the very end of the line, okay? So insertions always go this direction, all right? insertions. Deletions come from here. So I serve the first person, and then this person advances forward, so it can be served next. So this is called first in, first out. Applications of queues. Well, in computers, we do have many applications that actually are based on queues, like tasks waiting for a printer queues. Well, normally in a computer environment, we will have something like this. I will have a sort of networked environment where I have in my network many computers hooked up. So this is computer A, computer B, C, and so forth, let's say to computer Z. In my lab, I have one printer for my students. So the printer is actually somewhere here. All right? And students here are working on their tasks. They're either typing, let's say, their programs, typing their documents, reports, whatever. All right? And at the end of the day, they want to print out their documents so that they can turn it in to their instructors. So now A, let's say, finished working on his assignment, and he sends a job to the printer. Okay? C here finished his task as well, and he's going to send his task to be printed. Well, A had sent his request before. So basically, there is a queue in here for this printer. And as jobs comes in, they're going to go not directly to the printer to avoid the confusion, of course, on which paper belongs to which document. Rather, I'm going to put some sort of a queue in here. And as requests come from the different computers, I'm going to insert them into this queue. And now the printer is going to be looking always at the top of this queue. All right? And the first request is going to be served first, and it's going to be the whatever document, whatever task is going to be printed first. And then the request coming from C. After A finishes, I'm going to take the request from C, then the request from B, and so forth. So then tasks are going to be queued before they can be served on the printer. And this is a very common situation in real practice. Another example is tasks waiting for access to disk storage. Well, in the same analogy, assume that you're working on your computer, but this time you have plenty of applications opened. Let's say here's your computer screen. You're running Word for Windows, working on some sort of a document. You're running Excel sheet. I don't know, maybe you're running the email browser, the Outlook Express. 4 or 5, I don't know, maybe 10 applications, depends upon the situation you're in. Okay? And every once in a while, you're going to be saving your data. And your data is going to now go to the secondary storage, to the hard drive. Okay? Assume that somehow you clicked here to save, you clicked here to save, and you clicked here to save, and so forth. 5, 10, I don't know how many applications are sending the same request. They want to send some sort of information to be saved on the hard disk. Okay? And then it's the same way. The hard disk can serve one of these applications at a time. He cannot serve everybody at the same time. So basically, again, I'm going to have some sort of a queue in here. Okay? And the requests coming from the different tasks, the different applications, are actually going to be queued in here, one after the other. And then the hard disk is going to save these requests, save these documents as they come. So the first one who says save is going to be on top of queue, and it's going to be served first. After that comes the second application, third application, and so forth. So basically, several requests to go to the hard disk. Maybe for reading, maybe for writing, it depends. To read data, retrieve data from the secondary storage, or to save data to the secondary storage, whatever. Anytime you want to access the hard disk, okay, your request does not go directly to the hard disk, but rather it goes to a queue And that queue is controlled by the hard disk controller, as a matter of fact, to where it will organize these requests in some sort of a queue, and these requests are going to be served or performed in the same manner they come. First in, first out. The third application is processes waiting for the CPU in a time-sharing system. I don't know if you have knowledge about operating systems or not, but I can give you an idea. Basically, in the same example we were talking about in here, where I had many applications running at the same time on my environment, on my operating system, actually, basically these are just programs. And these programs, as you all know, consist of several statements, okay, in terms of machine language. All right, and each one of them represent a task to be performed on the hardware of the processor, therefore I cannot actually serve everybody as a CPU, as a central processing unit of the computer. I cannot serve everybody exactly at the same time. Well, we're having some sort of a multi-programming environment in here. That's true. Multitasks on a single machine. The way the operating system handles those people is that here's the hardware. And that's where all cooking happens, actually down here. And here are my applications. Application 1, application 2, up to, let's say, application N. Okay? They're all sending requests to be performed on the hardware. However, these applications, they don't typically in a real system talk to the hardware right away, but rather there is basically a layer, and I'm simplifying things here so you would follow me. There is a layer in here which is the operating system. And the operating system takes requests coming from all of these applications, okay? And there is an interface, standard interface between the operating system and the hardware down here. Okay, and basically I will have a task representing each of these applications, and that task has to be forwarded to the hardware. When do I forward it? Well, that all depends. Typically in a real system, a real operating system, let's say this application wants like 1 hour working on the hardware or on the computer. This wants another hour. This wants another hour, and so forth. We're assuming simple scenarios in here. Well, if I want one application to be performed fully on the hardware, then this application has to wait the whole time, waiting for application 1 to finish its task before it can start. Well, this could cause a long delay, especially for the application N, which comes at the very end. Instead of this, what operating systems do, they will divide the CPU time or the hardware time between those applications in what's so-called time-sharing system. So I would give a time slot to every application. The time slot could be 1 minute, 5 minutes, 1 second. I'm exaggerating with my numbers, of course, because computers are much faster than that. But for simplicity, let's say that the timestamp or the time slot is just 1 minute. That means this application needs 60 time slots to finish. Okay? I don't want this to stay that long and wait for that long till this application is done. What I can do is some sort of a round robin kind of thing. There are several in the operating system theory, several kind of policies that are used. But basically, let's talk about this round robin. I will give one shot to this application, okay, and then shot to this application, time slot to this. Work for one second and for 1 minute and stop. Give the application to a time slot here, okay? Give this application and so forth for all applications. And then when I'm finished with them, when I'm done with all applications, I go back again to application 1 and continue, okay? So basically, I'm gonna be having requests from every application to have time on this. Okay? Again, these requests to the hardware in coordination with the operating system in here, these requests are going to be entering some sort of a queue, and this queue is basically a line of tasks waiting for CPU time. And again, the microprocessor, the CPU, is going to be serving these tasks one after the other in the same fashion, in the same way they came in. So the first task is going to be performed first, second is going to be served after that, and so forth. So this is another application where we can use queues. In other application, one task may create subtasks. And this is normal, actually. And to explain it in more details, actually, we have to have knowledge about the operating systems kind of thing. But basically, when you submit your program to the processor, actually, your program could involve so many things inside it. So basically, to make life a little easier for the processor, it will divide this big task of yours, your program, into several subtasks. Now, some of these tasks have to execute in certain fashion, one after the other, as a must. And in that case, then I have to put these subtasks in the order they should be executed, okay, in some sort of a queue, and then the CPU is going to start serving these tasks one after the other according to their order in the queue. And of course, there are many other applications. Processes waiting for the CPU in a time-sharing system, as we said earlier. Basically, different processes submitted through the operating system to the hardware. And then we're going to have some sort of a scheduler that will schedule these processes one after the other according to their importance, according to their time of arrival, according to so many factors. As far as we're concerned in this class, these are well-defined tasks and they come at certain time. They cannot be given the access to the hardware or to the CPU right away, but rather they have to wait. Once we say they have to wait, then they have to sit in a sort of a queue before they can be served and their task is accomplished. And there are many other applications. Okay, let's go now in more depth into the queues and see how we're gonna process queues, how we're gonna manipulate the queues. The basic thing we're gonna talk about is how to append to the queue. This is the most basic operation that we do. Here's the queue that I have. And as I said, I already have entries in here. Okay? And I have a pointer in here pointing to the last entry in my queue. Now, append means to add an entry to the queue. That means I have a new entry in here. Okay? And I need to add this to my queue. So basically, this is going to go to the rear of my queue. Okay? And accordingly, I'm going to adjust this pointer to point to this last entry. So I append at rear at the very end as the very last entry in my queue. Well, I could have, in this case, a possible overflow. And we have talked about overflows when we were talking about stacks. Overflow means that the queue is full. There's no room inside this line to place this new entry. Simply because we have put a maximum limit on the number of entries I can have in there. And in that case, if I attempt to add a new entry to a full queue, then I'm going to face a what's so-called overflow. Okay? So before I can add, I need to make sure that there is a space inside the queue before I can add a new entry. Well, this operation is called append generally. However, in some textbooks, you might find the term enqueue. Enqueue means to add to the queue. Okay? So when I append, I go to the rear position and I add the new entry in there. Serve. Serve is the opposite operation, is when you take the entry from the queue. That's like the pop from the stack when we were talking about stacks. So serving goes from here, from the top of the queue, and I take it and serve it. Okay? Now I need to push everybody one position forward so that this entry is now on top of my queue. Okay? So then adding or appending to the queue goes to the very end. Serving means taking items from the queue. So serve means remove an entry from a queue. And as we said, when I remove from here, the very first entry that I have in the queue. Well, again, I could face the possibility of an underflow. And underflow means trying to serve people in the queue where you don't have anybody in there actually to serve. Okay, this is called underflow. The queue is empty and you're trying to get data from the queue. Okay? The term serve is sometimes called dequeue. So either we call it serve or dequeue, and append or enqueue. The append operation. The append operation is very similar to the push operation on the stack, to where you add new entries to your structure. However, the new entry is added at the end rather than at the top. So it goes to rear. Here is a picture, an illustrative picture of what we're saying. Here's my queue, and in my queue, in this example, I have two entries already in there. One of them is called A, the other is called Q. Well, actually, I have 2 pointers always in my queue. One pointing to the top element in my queue, and this is called front, and that's where I serve. And another one pointing to the last entry in my queue called rear, and that's where I add new entries. And let's say I have the function append here, which basically gonna add new entries to my queue. Here's a new entry called U, and he would like to stand in line waiting for service. Okay, then I'm gonna add it in the first available place in here. Front is not going to be changed, still pointing to this because A is still waiting for service. However, rear has to be adjusted so that it points to this new entry, because I have now a new entry and the very last entry in the queue is now this U. So rear is no more pointing to the queue, but rather it's pointing to this one. Okay? So then when I append, I adjust rear, front stays the same. Service operation. Serve is very similar to the pop, to where you take entries from your queue. However, as we said, when we serve, I take the first entry, first in, first out. In stacks, when I serve, I used to take the last entry on top of stack. It's different here. So if this was my queue, and I have 3 entries already waiting in the queue, waiting for service. Front is pointing to this entry, and rear is pointing to this entry. And now I want to serve. I'm ready to serve one of the people waiting in my queue. Okay, then this is the entry that I'm gonna serve. Okay, so this is popped or retrieved out of the queue for service, and I'm gonna adjust front so that it points now to this entry. Well, we would rather do this rather than moving the entries themselves, simply because in doing this, the cost for this is the cost of moving a pointer, which is a 4-byte quantity, from here to here. So instead of having my pointer pointing at this, here's my queue again, and I have these entries in my queue. Okay? Here is rear, and here is front. Okay? And now what I'm saying, servicing this entry. Okay, so this entry is going to go out of my queue. Well, the logical way of doing it after I serve this person, when you're standing in line in the bank or at the airport to purchase your ticket, everybody is going to move forward one step. However, in terms of computers, this is a very costly step, because who knows what is the size of these records. I could have in here huge records, a huge amount of data. So if I want to physically move this forward one position, that means I'm going to be moving a huge number of records in here to the next position. And that's in terms of computer time is very high in terms of number of computations. However, the easiest, this and this are simply pointers. And we all know already that pointers are nothing but 4 bytes worth of data, some number. Okay? So instead of moving physically the whole data in here, I would rather move this to point to down here. And that way, this is my front entry now, waiting for service the next time. Okay? So instead of moving physically the entries to here and to here, I will, instead of making front pointing to this location, I will make it pointing to this location now. So this is much more economical in terms of number of computations and in terms of computer time. Same thing, of course, goes for the case of rare. When I add the new entries, I will just move the rare pointer rather than moving everybody else forward one step. Okay, the notation we're going to use throughout this presentation and the coming 2 lessons is something like this. Q is some sort of a predefined type for queue, not for stack. And again, I'm sorry about these mistakes. I'll make sure that the team here change these and correct these mistakes accordingly. So I'm going to use the term queue the same way we used stack, as a matter of fact. Some predefined structure called queue. And then that's for the whole structure of the queue, the whole line. Now, each entry within the queue could have anything, like names, integer, floats, whatever. So instead of giving a specific example, we're just going to use the term queue entry, some predefined, again, data type, which basically describes the content of the entries inside the queue. And we have used this before, actually, when we were talking about stacks. So it's pretty much the same. Okay? So again, I'm going to use queue to refer to this whole structure. All right? And now, inside this structure, I have so many entries. Each one of these is of type queue entry. Okay. Based on this, let's again develop our prototypes for the different functions we're going to perform on the queues. Basically, a similar set of functions that we already developed for the case of the stack. There is a high similarity between stacks and queues, as a matter of fact. Let's start from the very first function, called queue initialization. The name of the function is create queue. And the goal behind it is to create the structure of the queue, okay, and reserve something in the memory for the queue. Nothing in there, it's going to be empty, it's just to initialize the structure. So basically, the prototype for it is of type void, function name create queue. I'm not returning anything as a return value of the function, but of course I'm returning the pointer to the queue structure itself. And in this, we're passing a pointer called queue of type queue, okay? And that basically is going to point to this. So the name of this is the small q in here. And I'm going to take in here, the maximum number of elements I'm gonna reserve for my queue. Okay, so like 100 elements, 1,000 elements, whatever. I put that as my maximum number in there. So as a result of this function, I will have, let's say 1,000 entries, I will have a structure somehow containing 1,000 entries of this type. Okay, this whole structure is pointed by Q. So Q is basically the name of my queue. All right, and I'm gonna initialize it to be empty, nothing in there. The precondition for this function is nothing, basically. We're starting fresh, nothing at all that we had before we get into this function. However, after we finish and return from this function, the queue will be created and it's initialized to be empty, nothing in there. So it's ready now for appends to come. Okay, along the way, similar functions. QEmpty, in many applications, I would like to check if the queue in hand has any entries in it or if it's empty. And like when we check to see if the queue is empty before I attempt to serve anybody in there. So definitely before I can serve, I have to check first. Are there anybody waiting actually in the queue or the queue is empty? So basically, the name of the function is QEmpty, and its return value is going to be of type Boolean, and this takes either a 1 or a 0. 1 for true, and the true is going to return if the queue is physically empty, no entries in there, or 0, indicating that no, there is somebody in the queue and the queue is not empty. The only argument it's going to take is the name of the queue, a pointer to the queue structure. The precondition, the queue has been created. Otherwise, I cannot actually go anywhere and check if I don't have the entity of the queue itself being created. The post condition, it returns true or false, according as the queue is empty or not. So if the queue is empty, I'm going to return true, 1. Otherwise, I'm going to return 0. Okay. Queue full. Basically, it's going to check whether the queue that I have is full of entries to where I can't add any more entries to it. And definitely, I need to call this function before I can append any new or add any new entry to the list. So again, the type of this function, the return value, is going to be of type Boolean, a true-false thing. And the only thing it's going to take is a pointer to the queue structure. Okay? And this time, I'm going to check how many items in there. If they equal to the maximum size, then the queue is full and I cannot do anything. Otherwise, then there is a space. Okay, so the precondition, queue has been created. Again, we're talking about an physically existing queue to check. Otherwise, of course, it's nonsense to do this. The post condition, after I return, I will return true or false, according as queue is full or not. So if it's full, then I'm going to return a true value of 1. Otherwise, I'm going to return 0. Other operations. Append. Append, as I said, is to add entry to the queue. And remember again, when we add at the rear of at the tail or rear of the queue, at the very end of the queue. And that's where you stand when you come as a customer in a line of customers waiting for service. The name of the function, we're going to call it append. And basically, it's going to be of type void. And it takes two things, actually. The entry that you would like to insert, and I'm passing it by value in here, because I'm not going to change the entries in here. Okay, I'm just going to put them in queue. The item which is going to be actually affected is the queue itself. And that's why I'm passing a pointer to the queue structure. So here is the entry that I would like to add to this queue in here. The assumptions made in here are that Q already exists and it's not full. Of course, because if it's full, then I'm going to have some sort of overflow. The outcome, the argument item, this entry, will be stored in the queue as its last item. The new entry, when I append, goes here. And according to this, the rear will be adjusted. Front is going to stay the same. However, the rear pointer will be adjusted to point to this new entry. The last function we would like to talk about in here is the serve. Serve is where you take or retrieve information from the queue. And again, we retrieve from the top of queue, from where front is pointing to, as a matter of fact. Therefore, again, this function is going to return void value. And it's going to take two parameters, the item and queue. However, this time, item is going to be changed. Basically, I'm going to take something from the queue and place it in item. So the value of item is going to be changed. That's why I'm passing pointer to item rather than item itself. And of course, the second parameter is the queue from which I'm going to retrieve this item. Okay? Again, the precondition is that the queue exists to start with, and that this queue is not empty. Otherwise, I'm going to have an underflow. All right? The post condition, after I'm done with this, the first entry in the queue pointed by front is going to be popped, retrieved from the top of the queue, and whatever contents in it, it's going to be placed in the memory pointed by item. And front, the pointer front, is going to be adjusted actually to point to the next item, as this next item is actually the next person aligned to be served. Okay? So when I serve, then I'm going to go to the top of the queue, take the entry, and adjust your front pointer to point to the next entry. That's it for today. I'm going to stop in here. Next time, we're going to continue on these functions and other functions, and we're going to get to the implementation of these functions. Of course, if you would like to review this material and see some other exercises, you will have to go to the UNINETTUno site on the internet, click on the MidNetU project, and you're going to find all the material you like in there. Thank you very much for watching, and we'll see you next time. Thank you.